You are listening to The Vocal Technologist. Spoken tech for your ears.
You know, usually when we talk about a major technological leap, there's this expectation that everything upgrades all at once.
Right, like the whole ecosystem just magically shifts together.
Exactly. Like if you invent a high-speed magnetic levitation train,
Yeah.
you obviously build the perfectly smooth, frictionless tracks to go with it.
Oh, yeah, for sure.
You don't try to run a 300-mile-per-hour maglev train on old, splintering wooden railroad ties from the 1800s.
I mean, it would just tear itself apart instantly. The physics just literally do not allow for that kind of mismatch.
Right. But when you look at what's happening right now in tech, specifically in the world of software development and AI, that is exactly what we are doing. Welcome to the deep dive.
It really is a massive mismatch.
It is. And today, our mission for you listening is to explore this incredible, massive tension in the tech world right now. We are living through this absolute acceleration of AI and coding speeds. We have the maglev train.
We definitely have the train.
But as we dig into the latest industry data and product launches and infrastructure reports from May 2026, we're seeing that train basically crash into some very stubborn physical, architectural, and quality bottlenecks.
Yeah, the friction is just everywhere right now. I mean, we have AI tools building software faster than at any point in human history, which is amazing, but generating speed is no longer the actual challenge.
The challenge is what? Just trying to contain it.
Exactly, trying to control it. We are suddenly having to manage this massive AI code bloat. We're literally having to rip apart and completely re-architect global voice networks just to eliminate milliseconds of lag.
Wow.
And at the exact same time, we're trying to keep all of this running while the physical internet cables under our oceans are constantly being severed.
It's just chaos. So, okay, let's start on the speed side of the equation because the sheer volume of output right now is just staggering. I was looking at the recent rollout from DigitalOcean at their Deploy 2026 conference.
Oh, yeah, the AI native cloud launch.
Right. They launched what they're calling an AI native cloud. And just to give you a sense of the scale here, they didn't just release a single new feature.
No, it was massive.
They dropped 15 different products across 5 integrated layers. So everything from base compute all the way up to specialized agent infrastructure. And it's all designed because modern AI agents are routinely processing hundreds of thousands of tokens in a single request now.
Which is wild. And processing that many tokens isn't just some technical hurdle, right? It's a massive financial hurdle.
Oh, because of the compute costs.
Exactly. If you have an autonomous AI agent scanning these huge databases and writing code, the compute costs can spiral completely out of control in literally minutes.
Right.
So that's why the most critical piece of DigitalOcean's launch is actually this thing called an inference router. It's essentially a mechanism built specifically to wrangle that financial chaos.
Okay, I want to make sure we really understand how this router actually works. If I'm following this right, it's basically like a rideshare app for data.
That's a good way to look at it, yeah.
Like if you need a package delivered, the app doesn't just blindly send a massive 18-wheeler freight truck every single time. It calculates the weight, the distance, how urgent it is, and then it might send, a bicycle courier or a sedan or a truck, depending on what's cheapest and fastest.
That is the exact mechanism. So when an AI agent sends a request, the inference router intercepts it.
Okay.
And it runs this real-time calculation, balancing cost, latency, and the required quality for that specific prompt.
So it's judging what the prompt actually needs.
Exactly. And then it dynamically routes it to the most efficient model. So maybe that's Kuhn 3.5 for a really simple task, or it bumps it up to DeepSeek v3.2 for something requiring complex logic.
Right, reserving the heavy hitters for when you actually need them.
Exactly. And the impact of that dynamic routing is huge. The sources highlight this case study on an AI company called Celiums.ai, and they cut their per token cost by 61% just by letting the inference router make those split-second decisions.
61%. That is incredible for the balance sheet.
Oh, it's game-changing for them.
But if the AI is generating code and processing data at a volume where we literally need algorithmic routers just to manage the traffic, how do human beings keep up with checking the quality?
Well, historically, they haven't been able to.
Right, because quality assurance, like QA testing, has traditionally been the slowest, most agonizing bottleneck in software development.
Yeah, and the industry is totally scrambling to automate that bottleneck away right now, just so human testers don't get completely buried under the sheer volume of AI code.
which makes sense.
So we're seeing this widespread adoption of platforms like Quase. And what Case does is it fundamentally changes the workflow.
How so?
Instead of having manual testers, automated testing scripts, and developer platforms all living in these separate silos, it integrates everything. It pulls continuous integration results and test automation directly into the native environments that developers are already using every day, like Jira and GitHub.
So it's essentially just trying to eliminate the dreaded weekly QA status meeting.
Basically, yes. And the data shows that teams using this unified approach are running their testing cycles up to 90% faster.
Wow, 90%. But I guess this is where we hit our first really massive reality check.
Yeah.
Because faster code generation and faster testing, they sound great on paper, but looking at the recent industry retrospectives on tools like Claude Code, they reveal a much darker side to all this acceleration.
They really do. The raw speed is a bit of an illusion.
Right, because AI agents definitely help engineers, especially senior engineers, I should say, spin up prototypes at absolute light speed. But that raw speed does not automatically translate into a better end product.
In many cases, it actually translates into a massive liability.
Because the AI doesn't have to deal with the consequences.
Exactly. AI agents don't feel the pain of maintaining the code that they write because it's just so effortless to generate like 10,000 lines of code in a few seconds. Developers are accidentally building these massive, overly complex, incredibly dense code bases.
Speed is basically being mistaken for quality. Let's unpack this with an analogy. Using AI agents to write all your code is sort of like giving a construction crew power nailers instead of hammers, but taking away their architectural blueprints.
That's a great way to put it.
Sure, the house goes up in a fraction of the time, but if you don't have architectural discipline or good quote-unquote taste, you just end up building a very sturdy, very ugly maze of a house.
Yeah, and not only is it an ugly maze, but to stretch your analogy a bit further, it's a house where all the electrical wiring is hidden behind solid concrete walls.
Oh, man. So you can't get to it.
Right. It becomes almost impossible for a human developer to go in later and fix a bug without having to tear the whole house down.
Which defeats the purpose of building it fast in the first place.
Totally.
Okay.
And this is fundamentally shifting what it means to actually be a software engineer right now. The primary bottleneck is no longer the physical act of typing out logic on a keyboard. The real bottleneck now is product taste, system judgment, and having the discipline to decide what not to build. The modern developer's job is really morphing from being a typist into being a ruthless editor.
That is such a fascinating shift, but code generation is really only half the battle here, right? Because if we are interacting with these AI agents in real time, like actually speaking to them out loud with our voices, we hit a completely different architectural wall.
Oh, absolutely. Voice is a whole different beast.
Because processing real-time, low-latency voice AI at a global scale requires an entirely different kind of infrastructure than just text.
It does. It requires a level of network observation and control that we haven't really ever needed before.
Yeah.
I mean, just to keep the text-based agents running without crashing, engineering teams are already having to adopt completely new observability tools.
Like what kind of tools?
So platforms like New Relic have rolled out specific AI monitoring. They call it A, and it essentially replaces traditional manual server telemetry with automated metrics, just to track how these autonomous agents are behaving in production.
Because you can't manually track an agent processing 100,000 tokens a second.
Exactly. But you're right. When you move from text to real-time voice, even a standard AI monitoring isn't enough. The underlying network protocols themselves actually have to be rebuilt.
And that brings us perfectly to what OpenAI just did. To handle their real-time voice AI at scale, they completely tore down and re-architected their WebRTC infrastructure.
It was a massive undertaking.
But wait, I need to push back on this for a second. WebRTC has been the backbone of browser-based video calls for, what, over a decade?
Yeah, a long time.
We use it for remote meetings every single day, and honestly, it works fine. Why did they have to tear down a protocol that already works?
It's because of who, or rather what, you were actually talking to. Standard WebRTC is fundamentally designed for peer-to-peer communication.
Meaning human to human.
Right. It's designed for your laptop directly talking to my laptop.
Yeah.
But with voice AI, you aren't talking to another human client. You are talking to a centralized, massive compute cluster. And standard WebRTC fails at that AI scale because the process of terminating the network connection and the process of routing the data packets are deeply tangled together in the protocol.
And that tangle creates lag.
Exactly. When you try to force that entangled process through massive cloud architectures, it creates unacceptable conversational lag.
Okay, so standard WebRTC ties the routing and the connection together. If I'm understanding this right, OpenAI essentially had to decouple the post office from the mail carrier.
That's a perfect analogy.
So how did they actually pull that off technically without completely breaking the protocol?
So they split the architecture into two distinct pieces. First, they built this very lightweight relay layer that sits way out at the edge of the network, and its only job is just to catch the incoming traffic.
Okay, the relay catches it.
Right. Second, they built stateful transceiver services deep inside their cloud to actually process the audio.
But if they're split apart, how do they connect?
Well, the genius part is how they get the data packet from that edge relay to the correct internal transceiver. They embed routing metadata directly into something called an ICE username fragment.
Hold on, ICE username fragments.
Yeah.
ICE stands for Interactive Connectivity Establishment, right?
Got it.
But that's normally just the protocol used to help peer-to-peer connections punch their way through stubborn corporate firewalls. Are you saying they hijacked a firewall punching tool and used its username field as like a sticky note for internal cloud routing?
That is exactly what they did.
That is wild.
It's incredibly clever. By injecting that metadata into the ICE fragment, the lightweight edge relay instantly knows exactly which transceiver cluster to forward the audio to, and it does it without having to process the heavy protocol itself.
Wow.
And the ripple effects of this decoupling are just huge for them.
Right.
First, it drastically reduced their public UDP surface.
Which is important for security, right?
Oh, massively. Instead of needing one open network port for every single voice session, which is a total security and scaling nightmare, they reduced it down to a small, fixed number of ports.
Okay, that makes sense.
And second, decoupling those layers meant they could deploy the entire transceiver backend natively on Kubernetes, which allows the whole system to scale up and down dynamically based on demand.
But the most noticeable result for you listening, like the reason this actually matters when you open your phone and talk to an AI, is the geographic placement of all this.
Yes, the global reach.
Because those relays are so incredibly lightweight, OpenAI deployed ingress points all over the globe. So when you speak, your voice packet doesn't have to travel across an ocean just to figure out where it's going.
Right, it doesn't have to make that huge journey first.
It enters the network right in your neighborhood, which dramatically reduces the first hop latency. That is the hidden mechanism that removes that awkward walkie-talkie pause when you converse with an AI.
Exactly. It creates this illusion of instant presence. They've built this incredibly sophisticated low-latency global network that makes the compute cluster feel like it's literally sitting in the room with you.
It's absolute cloud magic.
It really is.
But, and this is a big but, all of this cloud magic, the Kubernetes clusters, the global relays, the massive agentic AI operations, it ultimately still sits on dirt, wires, and concrete.
Yes, it does. The physical layer.
And looking at the recent data, that physical layer is shockingly fragile.
It is. The contrast between the ethereal, floating nature of cloud architecture and the brutal vulnerability of the physical world is just stark.
Yeah.
If you look at Cloudflare's analysis of internet disruptions in the first quarter of 2026, the global internet took a heavy, heavy beating.
I mean, reading the report, it feels like a disaster movie script. The data shows massive outages caused by severe weather events, wiping out regional connectivity, power grid failures taking entire data centers offline, and underwater fiber optic cables being physically severed, which severely impacted traffic across the US, Europe, and Africa.
The physical infrastructure is so exposed.
It really is. And looking at Cloudflare's data objectively, we also see major disruptions tied to geopolitical events.
Right.
Now, before we list these, we must explicitly state that we are impartially reporting the contents of the Cloudflare report. We are not endorsing any viewpoints or taking any sides here.
Absolutely, just looking at the data.
Right, but the report details government-mandated internet shutdowns in places like Iran, Uganda, and Cuba, as well as physical damage to cloud infrastructure due to military conflicts in the Middle East. So, regardless of the politics of any of those global events, the raw infrastructure takeaway for an engineer is undeniable. The physical layer of the internet is incredibly volatile.
Highly volatile. And that volatility completely changes how you have to build software today.
Because you can't rely on the hardware.
Exactly. If you are deploying a global AI infrastructure, you cannot assume your server will even have power in 10 minutes. You have to assume the physical cable connecting your database to your user might get severed by a ship's anchor at literally any moment.
Which is terrifying.
It is. So systems can no longer be static. They must be entirely self-healing and dynamic.
Which perfectly explains the huge surge in dynamic workload tools we are seeing right now. The software essentially has to learn how to dodge physical bullets.
Exactly.
For instance, Amazon CloudFront just rolled out a new cache tag invalidation feature.
Which is really cool.
Yeah, so if a data center goes down or content needs to be purged immediately, developers can now remove related cached objects globally with a single request in under 5 seconds. The network has to pivot instantly just to maintain efficiency.
And to build on that need for flexibility, AWS also just launched something called EKS hybrid nodes. And this perfectly illustrates that exact tension between physical hardware and the cloud that we're talking about.
Let's break down what a hybrid node actually does for the listener. It's essentially a free open-source gateway deployed via Helm onto EC2 instances.
Right.
So in simple terms, AWS basically built a bridge. You drop this piece of software onto a physical server sitting in your company's private basement, and it automatically handles the complex networking required to let that basement server talk to a massive cloud-based Kubernetes cluster.
Exactly. It bridges that physical-to-cloud gap without requiring a human network engineer to go in and manually configure the routing tables every single time a workload shifts.
That saves so much time.
It does. The cloud pod and the on-premise basement server act like they are literally in the same room. But, and this is the catch, creating these highly ephemeral systems where a piece of code might spin up in a cloud cluster, process an AI prompt, and then terminate 30 seconds later, it creates a terrifying security environment.
Oh, I bet. Because how do you secure a workload that only exists for half a minute? You can't just run a weekly security scan on that.
You can't. A recent report from Sysdig on Kubernetes security highlights this exact problem. Traditional posture-based scanning, which is basically just checking to see if your server is configured safely, is no longer sufficient.
Because the environment changes too fast.
Exactly. In these cloud-native environments, attacks happen in seconds. You need runtime-focused security.
Meaning security that watches while it runs.
Right. You need tools that are actively monitoring the behavior of the software in the exact moment it executes.
Yeah.
Because by the time a traditional, weekly scan actually runs, the vulnerable container and the attacker are already gone.
It's literally like trying to secure a ghost.
Yeah, really is.
Okay, so we've looked at the massive scale of the cloud. We've looked at AI agents writing thousands of lines of code, the voice architecture spanning the globe, and the very physical reality of severed cables and power grids. Let's bring this all the way down to the desk of the individual developer.
Yeah, the actual hardware on the desk.
How are they physically accessing all of this power?
This brings us to a really fascinating piece of hardware. The newly released MacBook Neo.
The Neo.
Yeah, it is Apple's cheapest Mac to date. It retails at just $599. And it perfectly encapsulates everything we've been talking about regarding the friction between our high-end software ambitions and the stubborn laws of physics.
The Neo is such an interesting little machine. Internally, it uses the A18 Pro chip, which is an architecture derived directly from the iPhone.
Right, it's a mobile chip.
So if you're a casual user, you get this incredibly premium build quality, fantastic battery life, and really snappy, bursty single-core performance. Like opening an application or loading a web page feels lightning fast.
It feels great for about 5 minutes, but the moment a developer tries to use it for serious engineering, they hit a complete brick wall of trade-offs.
The limitations are pretty severe.
Yeah, the machine has a hard, non-upgradable 8 GB memory limit. It has a notoriously weak port selection. But most critically, it suffers from severe thermal throttling under sustained workloads.
Let's explain what that actually means for anyone who hasn't experienced it. The Neo is essentially a massively powerful smartphone brain shoved into a passively cooled laptop chassis, meaning there are absolutely no internal fans to blow the hot air out.
Right. There's nowhere for the heat to go.
Exactly. So the moment a developer tries to compile a large, complex code base or run a local AI model, that chip starts generating intense heat. Physics takes over. And to prevent the silicon from literally melting itself, the computer artificially chokes its own processing speed.
It forces itself to slow down. So you end up with a laptop that is fantastic for a college student writing a term paper, but it is practically unusable for sustained software development, heavy creative rendering, or gaming.
And the irony here is just so thick.
It really is.
We have autonomous AI agents in the cloud that can write code at light speed and route hundreds of thousands of tokens dynamically. But a human developer sitting at a desk can't even compile that code properly on a brand new entry-level Apple computer because the metal literally gets too hot.
It's hilarious in a way.
Which answers a question I have had for a while now. Is this severe hardware bottleneck the reason why developers working on the most advanced AI systems in the world are still obsessed with a text editor from the 1970s?
It absolutely is the reason. You're talking about the Vi family of text editors, right? Like Vim or NeoVim.
Yes, exactly.
It is perhaps the greatest irony of modern tech. A Vi was created in the 1970s. It has this notoriously brutal learning curve where you navigate the screen entirely through arcane keyboard shortcuts instead of using a mouse.
Right, it looks terrifying to a beginner.
It does. Yet it remains wildly popular among elite engineers today.
I mean, you walk into a startup building the absolute future of artificial intelligence, and the lead engineer is furiously typing into a black, minimalist terminal window using commands invented before the personal computer even existed. Why does this ancient tool survive?
Because Vul is the ultimate software cockroach.
I love that, the cockroach of code.
Seriously, it survives everywhere, precisely because it completely ignores modern trends. It is incredibly lightweight. It uses practically zero system resources.
Ah, so it doesn't heat up the machine.
Exactly. That means it will run flawlessly on a thermally throttled, passively cooled MacBook Neo, and it will run exactly the same way through a remote terminal on a massive cloud server. It requires no heavy graphical interfaces at all.
It just works.
And once you master those keyboard shortcuts, it enables a level of high-speed surgical text editing that modern, bloated software applications just can't match.
It really proves that while our ambitions and our hardware limits are constantly clashing, foundational, resource-efficient tools never really go out of style.
They never do.
Okay, let's pull all of this together and summarize this deep dive for you listening. We are undeniably living in an era of light-speed acceleration. The software train is moving faster than ever before.
Oh, without a doubt.
We're seeing DigitalOcean's inference router instantly /AI compute cost by 61%. We're seeing OpenAI entirely decouple and re-architect the WebRTC protocol to eliminate real-time voice lag globally.
Incredible feats of engineering.
Truly. But on every single front, that speed is crashing into bottlenecks. We are bottlenecked by vulnerable physical infrastructure like power grids and severed ocean cables. We are bottlenecked by hardware that physically overheats when pushed too hard. And perhaps most importantly, we are bottlenecked by our own human capacity to maintain the sheer volume of code that AI can now generate.
And, that friction leaves us with a really critical thought to consider.
What's that?
As AI agents continue to generate more raw output, more logic, and more data than is humanly possible to read, while our physical world remains stubbornly bound by weather, heat, and power limits, the fundamental role of the developer is shifting.
Shifting away from just writing.
Exactly. Moving forward into 2026 and beyond, will the ultimate highly paid skill of an engineer look less like the rapid writing of new code and much more like the ruthless surgical deleting of a VMaster?
Wow.
Will the future actually belong to those who know how to prune the endless bloated output of the machine back down to a clean human scale?
I love that perspective. The real superpower isn't figuring out how to build the maglev train faster. It's having the discipline and the taste to know exactly where to lay the tracks so the whole system doesn't derail. Thank you for joining us on this deep dive. Take that thought with you, keep questioning the systems around you, and we'll catch you next time.
Spoken Tech for your ears.